Welcome. This is Professor Nathan Weezy of Marquette University. This is going to be a section of digital control power electronics called the Proportional Integral Derivative Controller, or better known as the PID controller. In equation 1, we have defined the PID controller in the Laplace domain. We have a constant term, we have an integral term, Ki by S, and we have a derivative term, Kd by S. And when you're designing a controller, your goal is always to find these three gains, Kp, Ki, and Kd. All right, let's take a look at what the PID controller actually contributes to the overall system. If we just do some simple algebra on equation 1, you can rearrange stuff, get common denominators, and get this equation here in 2. And what you will note is that the PID controller contributes a pole at the origin. That's great because that's an integrator. It'll help us get rid of steady state error. And 2, it contributes 2 zeros. And depending on these ratios of Kp by Kd and Ki by Kd, you could have two real valued zeros, or you could have a complex pair value of zeros. Just depends on how these values are selected. Okay, so you have one pole at the origin, gives us 0 steady state error, and 2 zeros. Could be complex, could be real valued. Okay, if you solve for the zeros, which is solving the numerator of equation 2 using the quadratic equation, you get this. Now, it depends. A lot of times PID controllers are used where you have your plant has a lot of phase loss to it, or lag, and you need those zeros to bring the phase back up. PID controller is pretty easy to mess things up because it's very susceptible to noise, especially when you're taking derivatives. And it's very susceptible to making systems unstable because of you have 2 zeros. Okay, so when you design with these, you generally have to be very careful with what you're doing and understand what you're doing to the system. Okay, so what we're going to do is apply this to a plant, and I just have an arbitrary plant here in equation 4. What we're going to do here is try to look at different values of Ki, Kp, Kd in order to stabilize this. Okay, so this is our plant. We're going to try to look at some values for this. This thing has 2 poles already, the plant, one at -3 and one at -1. If you take a look at this system, it's already stable as is. But we'd like to be able to control it, meaning put a reference in, control it to be whatever we'd like it to be. So what we're going to do, the first step at this is to just show you how we can make a really stable controller and a very fast controller with kind of infinite bandwidth if we want. And how we're going to do that is we're going to take these 2 poles and we're going to cancel these 2 poles with the 2 zeros of the PID controller. So if we do that, what we're actually going to end up doing is setting 4 equal to Kp by Kd and 3 equal to Ki by Kd. And if you go ahead and do that, you will cancel out. Let's do this with this. You will cancel out these 2 terms. And guess what you're left with? Kp 25 by S, and that is just an integrator now. And this is really easy to set your bandwidth now. So you can solve this for the bandwidth, which will be just Kp 25 by omega. We'll set this equal to 1, where omega is equal to 2 pi, what did I say, 100 hertz. So you can find the Kp now. If you do that, this is what you come up for Kp, comes out to be 8 pi. Once you have Kp, you can solve for Kd, and once you have Kd, you can solve for Ki. So if you do all that, these are the 3 values for Kp, Ki, and Kd. And this is with a pole cancellation method. There's many ways to do it, but this is just one selection of 3 variables for Ki, Kp, and Kd that will give us a controller. Now the resulting controller looks like equation 8 if you plug in those values for the 3 gains. And what we're going to do is sample at 1 millisecond and convert this to a Z-domain controller, discrete time controller, using the Tustin approximation. So we just took essentially GC of S, this equation here, and we used the Tustin approximation for S, and we solved for GC of Z. Okay, so this is what our controller looks like. Now we can look at the closed loop transfer function by doing GOL. This is back in the Laplace domain. GOL over 1 plus GOL. And we'll get 628 by S plus 628. And again, you can convert this closed loop response to the time domain with the Tussin approximation again. All right, if you do that, look where our lonely pole is at 0.728. Oh, that's actually really good. So we look at it, here it is, 0.728. You can see it here, 0.728. We're on the damping line for 1. So this is awesome. Damping's 1. This is going to be a nice response. And the bandwidth, just so we look at this, is 0.1 pi by t, approximately, roughly. So that's where we're at. So it gives us a response relative to the sampling time of how fast our controller will respond. So here's the step response for this controller, and this is a pretty good response. The solid line is, of course, the continuous time response, and the dashed line here is our digital controller response. All right, very interesting. Now, that was pole cancellation, and sometimes you can use it to your advantage, sometimes you can't. If you have a plant where these things move on you, they can move a lot over time, and the time could be short. It could be seconds, or it could be over the lifetime of the product, think years. But if it's going to move on you, then pole cancellation could potentially get you into trouble. The poles could stop canceling if these values change, and then you could get some roots where you don't want them to be. For instance, low damping or near unstable edges in the pole zero plot. So what I did here is, here's our controller now. Let's consider the design space for Ki, Kp, and Kd. You essentially have a 3D matrix of infinite values for those. So how do we start to begin looking at that space? Well, we're going to do a root locus plot, which we did before, and we're going to fix 2 variables and sweep 1 and see what happens. So how I did this is I started off with fixing Kp to be 0.582. This is going to be for the blue line, so I should probably write this in blue. I fixed this to be this, 0.582. And then what I did is I also fixed the ratio Kp by Kd to be 1 and Ki by Kd to be 1. And what I did then is I swept the various ratios here. So I swept, in this case, I'm sweeping Kp while maintaining these ratios. The dot that I have right here is actually for a fixed point here. Okay, so if we look in blue, blue is actually really hard to see because it's in here. It doesn't move a lot. It looks something like this. They're zoomed in way in there. That's where those plots are. Now red, orange, and purple, the only thing that I'm changing is the ratio of Kp to Kd, and I'm sweeping again Kp. What happens, for instance, in the red one is they start in here and they come out like this. One goes in here, and this one comes out and goes like this as you sweep Kp. Same thing happens for the other one. So we come in here like this. This other one comes out like this and goes this way. And lastly, we have our purple one, which will go out and come in like this. And this one will come out and go out that way. Okay? So those are kind of the trajectories of the root loci. Now, this is in the S domain. So remember, going this way to the left means faster response. Going out in these radial directions means less damping. You can see our damping lines, like this line here would be damping of 1, while this one over here is 0.5. It's a very small amount of damping. So we'd like to be to the left and on the x-axis is what we'd like to be. Okay, what I've done is I've calculated some values, and I want to look at the type of response that I have here. So I picked Kp to be 0.582, and I simulated some of these poles. These are the poles for the 4th controllers that I am selecting. you can see that this ratio here is the Kp by Kd. See, I have 1, 10, 20, and 30. This is my Ki by Kd. It's set for 1 for all of these. And so what I'm going to do here is look at these 4 controllers' responses. Now, this is really interesting. What happens here is that I have 4 different responses, and this blue one looks kind of strange here. So in purple here, this is an underdamped response, right? It rings out, takes a while, but it gets there. We have the purple here, the yellow, the orange yellow. This one will come up and down. It's a little better performed. The orange in here looks pretty good. And then we have this really slow blue one. That'd be this one. Okay, what's going on here? Let's relate this back to the root locus plot. Well, if you remember, I was talking about the blue poles. If you go ahead and see them, they're all in here. They're located in here. You'd have to zoom way in to see them. But essentially what's happening is the poles closest to the imaginary axis dominate the response. Well, the farther they are this way to the right near the imaginary axis, the slower the system is, which makes sense here. Actually, this is quite slow. Some of it comes up, about 80% of it, but then another one of the roots comes in and takes a really long time to respond. So what happens is you have this complex pair pole here, but you have this one. This one's going to dominate, but this one will go up right away. So this is why we have this slant, which is kind of fast, but then we have this, and it takes a long time to get up to 1 because those are those poles that are really slow to react really close to the origin. Now, we don't have that problem with these other 3 sets of Kp, Ki, and Kd values because their poles all come over here to the left. For instance, we have these values over here that are dominating this response. Here, here, and here. Now, you can see as we go this way with purple, we're getting less and less damp. This is 0.5. This line's essentially 0.5. This is 0.45, 0.56, etc. So you can see as we get closer again to the x-axis, we have more and more damping, which is what we want. Okay. Now, if we convert these to the z domain using the Tustin approximation, so we can take these 4 controllers and convert them to their digital domain equivalents using the Tustin approximation, we'll get equations 17, 18, 19, and 20. Now what we're going to go ahead and do is just calculate the step response of these 4 and investigate them. And if you take a look at these track very well with the time, continuous time variant response here. Again, the blue one's way behind just because of where the poles were on this plot. And at least out of these 4, the red one is probably the best response. It overshoots a little bit. We could probably get better dampening if we spent more time exercising the root locus and looking for better combinations of Kp, Ki, and Kd. But this is the response we have. The digital domain looks pretty good. I don't think we're going to have any instability due to converting from continuous time to the digital domain. Now, what I'd like to end up with is we just quickly talked about the sweeping all these values in the root locus, and I only did a really small subset. So if you look at this, what I did is I swept Kp in this diagram. I swept Kp while holding these 2 ratios constants. Okay, so all of these points on these lines are different Kp with these constant ratios. And this ratio here, this 0.8582, responds to these discrete points that I picked for plotting their step response here. Now, what I'm going to say is I just arbitrarily picked these. What you're really going to want to do is a more exhaustive search, which means that you're probably going to want to pick more ratios here, right? And again, I only did a couple of those ratios. You're going to want to do more ratios here. I only did 1. And then, of course, once you do that, you'll have a better view of what the space looks like in the estimate in terms of the system poles. So essentially what you're going to do is you're going to do a bunch of root loci with sweeping 2 ratios and sweeping KP for each ratio combo. And what you'll do is you'll get a bunch of more lines on here, and you're going to find some sweet spots. Where are the sweet spots? Well, the sweet spot in the estimate is to be on this axis because you have really good damping, right? Your damping ratio is 1. And then it depends on, how fast you want to be. Fast you want to be, you want to go to the left. But what you'll do is identify a group, a subgroup of ratios that, for instance, let's say I wanted to be around here. You'll identify a group of ratios that are very good for this area. And then you can design your controller to have those values. Okay, and this would be a more exhaustive workflow, and you could definitely do it pretty easily in MATLAB. This was all generated in MATLAB, save you a lot of time. But in general, this is how you want to explore the solution space for where you put your controllers for a PID. All right, this concludes the PID discussion for digital control and power electronics. Thank you.